first off, kicking us off, is Tim Santos, who's a Director of Developer Relations at Graphcore. So for those of you that don't know, Graphcore is a company based in Bristol that actually develops really interesting hardware for actually running or crunching the numbers on silicon, basically. And Tim, I think, will be telling us a little bit more about that. Tim's worked in a lot of different roles, from what I can tell, from kind of a researcher type areas all the way through to kind of handling these kind of big machine learning type operating systems and things like that. And so I'm going to hand over to Tim to tell us a little bit more about why we might need an AI processor.
Yeah, hello everyone. Good afternoon. Thanks for having me, Gene Golding Institute, and also really good talk from our speakers, Neil. Tough act to follow. But yeah, so I'm here to talk about why we need a new AI processor. Just a little bit of a background, who we are. So our mission as Graphcore is to deliver the world's best processors, and if you create the processor, on top of that, software tools to support the next breakthroughs in machine intelligence. I think I picked up, like Neil mentioned earlier, that our purpose here is to find like to work together and build the solutions, and try not to what was that? I think build the next innovation, the next kind of things in machine intelligence and beyond. And I'm coming from both the hardware, software, and platform. So because we build the processor, so everything on top of that gets built. And so when I was thinking about the topic, this is the question that came to me. Like when I think about why even bother, right? The last decade of advances in AI accelerators, in the incumbent hardware, has brought us to a lot of advances in models, algorithms, models getting larger from 175 billion parameters, GPT-3 a couple of years back, last year, Megatron, 530 billion, and so on and so forth, right? Like if something's not broken, why fix it? But yeah, so that's why do we bother? So I think the question goes back to like the types of solutions with the current hardware and architecture. A lot of insights. We got a lot of insights about like how we process, we humans process information, what is intelligence, and so even this graph is a simplification, an oversimplification. We talk about a number of parameters. Like why do we even talk about that, right? So are there other types of algorithms and even different ways that we could represent information, and of course different ways to process those different information data structures. So the current so these models, growing numbers of parameters, mostly involve dense computations. We need new types of approaches, and we talk a lot about that. So this is an article from Google a couple of years back about the hardware lottery, which says, a research idea wins because it is suited to the available software and hardware, and not because it's the idea the idea is superior to alternative research directions. So I remember when I was doing my MRes, it was like my supervisor was working in speech, and he is a proponent of biologically inspired features, like visual features, audio features, and it's one way of doing something, and then now the deep learning, neural networks, the models that we use are different ways of getting to the same same thing. And it's a byproduct of the current hardware architecture and the current hardware. So, I mean, I would just call this like the proverbial hammer. The solutions that we have is just, you know, the hammer to the the nails to the proverbial hammer of the current architectures, right? So yeah, I know some of the insights on like how human intelligence works, how they're represented, what types of compute are done. So these are new types of computation workloads that are being explored and experimented, and they require different. They have a different requirement, such as massive parallelism, of course. So growing numbers of parameters, sparsity in data structure, like the world is represented in very sparsely, right? Like I remember like we talk about unstructured data as text, but then we convert it into a matrix eventually. So because the current architecture, the current hardware doesn't deal well with sparse data. Real world information, they like some relational aspect of real world applications, how we interact, how we perceive information and react to it are sparse. So you could represent them in graphs, and you know certain things like if I think about, you know, the brain, and people talk about we're gonna be having X amount of compute. That's one way of seeing things. Like you have to have the compute power to be able to run those. But the way brain would it's like if it's like the analogy of like matrix multiplication of all neurons firing up. It's like it's like all neurons are firing up, right? Like we don't process information like that. So certain parts of our brain are rooted. Information is rooted through our brain. Not everything is all running all at the same time. So that's one characteristic of how our brain functions, right? And these kind of behavior and representation are one of the reasons that you know we have created a new type of processor. So and it's not. I think it's not a way to sort of replace the incumbent. So they perform well in certain tasks. Certain models perform very well. It's just like we have like, you know, multiple intelligences or different sensors. We sense our world differently. So I think it would be something similar to that, right? We create a new hardware to open up the search space for new types of algorithms, new types of solutions. So CPU, for example, is really good at scalar calculations. GPUs are good with vector calculations, with like single instruction on parallelized data running on multiple data chunks. And so what we have done is we have explored and we have created and designed the intelligence processing unit that functions well on graphs, massively parallel compute, and to enable as well like fine-grained parallelism. I mentioned earlier, right? Like GPUs would be running like you have your data parallelism. You're running the same a single instruction on multiple data. But so one of the design decisions that we have done is to come up with this multiple instruction, multiple data. Basically, you've got here, for example, one processor has 1,400 cores running their own. It's like you have your 1,400 computers running different types of instructions in different pieces of the data set. That would allow you to have sparse computation, graph. They work well with graph compute. So yeah, so this is why. This is one of the reason that we have. So as I mentioned earlier, okay, so scalar CPU, GPUs for large blocks of dense contiguous data, and massively parallel and high performance for new types of models. So yeah, and these design decisions are all done to sort of just open up to new types of compute. So here's some of the information, technical specs on the intelligence processing unit, and I think one proof this allows us. So I'm showing this chart because this is the efficient net model and like speed. It's a good example of a new breed of model where you're not just pumping in a lot of parameters, a lot of parameters, but more of an efficient way of designing your network. So it's going to be smaller in terms of memory consumption, the size of the model, but it's more efficient. And what we have seen is that in the incumbent architecture, in the incumbent hardware, is that it doesn't perform very well. That's why there's not a lot of exponential increase in the types of these types of model. And this is, I think, like one. This is the promise that is a promising result, something that we are looking to bring into to the research space, to the AI space as well. So, and with this type of opening up to new breeds of models, there are we have seen like different use cases and how they could potentially be used. I've mentioned earlier, like a lot of like real-world data is represented through graphs. There's a lot of sparsity. For example, so consumer internet, finance, healthcare, research, and automotive data center. I'll just go through some of the use cases where we have seen that a new type of hardware, a processor, works well in real-world use cases. So, in healthcare, for example, drug discovery, the way proteins are represented and how they would, like a medicine would bind to a certain protein. These are not the well-performing models are more graph type of models like GNNs and that sort. And we have seen that the new type of hardware, the IPUs, work really well with these type of workloads. So other types like patient data processing, preserving information, like data privacy, new types models such as federated learning and differential privacy, wherein you have a lot of different independent cores. We have seen that in the IPs where you have a lot of different cores running independently on different data set. So these are like potential workloads in that space wherein the IPUs work well. And so here's one of the use cases wherein the IPU has enabled like faster iteration of experiments, hence like a broader, like a better it's the speed of iteration of experiments allows you to have more experiments, running in your very short time frame, and gets you to maybe clinical trial faster. So one case study here is with Lab Genius, where they used BioBERT, real-time simulation-based inference, so wherein you have massively parallel compute that requires like low, high throughput, low latency type of workloads. So this is one of the use cases where it like our hardware has shown like at least 7.5x faster. This is the use case I mentioned about differential privacy. And it's not just the enablement of a certain type of model, but also making it production deployment ready, or making it possible to deploy these models into production. Because yeah, if it takes a very long time to process your information using these type of models, then it might be that the information or an inference or a prediction is already stale. So again, this is an example of the EfficientNet model, new breeds of model that I mentioned earlier. For forecasting, so again, the massively parallel compute enables low latency inference for weather forecasting. Like Dan mentioned earlier, like the complexities of weather and climate data, and other things. So as well, like flood prevention, climate, ecological governance. Again, solving real-world problems, having a new type of processor to use different types of new types of models. And I mentioned earlier that we talk a lot about the number of flops, the size of your hammer, right? Like we're growing, we have bigger, faster, stronger processors and compute, but also having a new, making it general purpose and enabling different types of model exploration. So again, this is one of our roadmaps to brain scale AI. So the scale with the numbers of potential neurons represented, but at the same time having that flexibility of sparsity and graph computation. So it's not just enough that you have so much flop that a compute that can run X amount of flops, but also have different like workload schemes or execution paradigms and parallelism paradigms. So yeah, so that is our again just a summary of what I talked about. Why do we even bother creating a new hardware? So AI models of the future will become increasingly expensive. So I think one of the things that you would notice in the chart of like X number, the billions of parameter models, is that these are released by your bigger large companies, and like a GPT-3 is, for example, is like 10, 20 million to train. But yeah, the summary is that AI models of the future will become increasingly expensive and complex to work with. So that's why that's why we bother creating a new type of hardware. So that's any questions? Thank you.
Thank you, Tim. So we've got 2 or 3 minutes for some questions. So are there any burning questions that people have out there?
Hello. Except the processing power increase with the APUs, is there like an investigations of reducing the power consumption from the processors? to reduce the cooling demands and all those kind of things.
Yeah. So I think a nice analogy is the, all neurons firing up, right? Like the brain is a very efficient machine, right? So in sparse compute, for example, not everything is firing up. So you're in a way, that is one way of having a more efficient efficient workload. So the efficient, for example, in even having you have lower memory footprint, you train faster, then you are spending less less time, less power in these kind of workloads. So that's one of the. So I'm just thinking about, like, for example, if you're representing a sparse data point, you are like masking it to fit it into a matrix or vector, right? So that's not very efficient if you're all running compute in that aspect, right? Like so one is like having that faster type of models running on different workloads would help you with that. Yeah.
Okay, thank you.
Brilliant. Any other questions for Tim? Yeah.
So the case studies you showed were using traditional models, whereas I guess it seemed like a key feature of processor is that you have thousands of different types of program running at once. Yep. Are there some speculative advance in AI you're looking at already that might be 1,000 times faster in your processor to take advantage of the fact that you can have so many different types of program running at once?
Yeah, so those are like the type of, so we haven't, like mixture of models, for example, are one very strong candidate for the hardware. So what we did for starters is create the new type of architecture, and we partner with researchers to sort of, help us know what we don't know, or help us know and discover what works well on certain, on our hardware. Just like how, a decade ago when we found out that neural networks work well on GPUs, right? So there's also that unknown yet but the mixture of models and different workloads. Just thinking about the MIMD architecture actually is one strong point that but we believe that the hardware works very well with.
Okay, we've got time for one very quick question. If not, I'm going to ask a question myself. So I come from a biological side of sort of computing in a way, and in biology you see a lot of diversity in how things are computed or processed. And it was quite interesting seeing the different types of architecture. What do you foresee as the future? Do you see it as lots of different specialized computers, or some very clever general purpose computer that you might use?
I think, that's so. The efficient net example use case actually tells you that, you can achieve the same performance by designing better, more clever algorithms. So we're going to hit a limit of like how much processing power we could generate, or even how much data you can pump in. So the healthcare data, for example, I know I've had some conversations yesterday about like they're not gonna go the big data route wherein you pump in, because those billion parameter models requires tons of data, and this is where your clever biologically inspired models, wherein you have unclean, sparse data, or you're getting you're inferring an attribute from another data set or something like that, right? So I think there's just no way to sort of go, but to have these smaller data with more efficient and more biologically inspired, I guess. So there's a big research based on biologically inspired models and neural networks, for example. So,
thanks very much. So let's thank Tim one more time.